We're going to look at what the GPU is and how it can be used for concurrent programming. I'm going to have a quick think about threads and parallel computing and understand the difference between a GPU and other GPUs. So let's start off with that. So we already know that the graphics processing unit will do graphics. We know that it will do 3D graphics, things like that. So that's kind of commonplace knowledge. What we don't necessarily know is how a graphics processing unit is different from a central processing unit. The CPU is general purpose. That means we can use it for a variety of functions. We can use it for any kind of day-to-day computing need. It tends to be very good at normal integer mathematics because that tends to be used more in day-to-day computing. It can do floating point calculations, but it tends to be focused on integer. Depending on the CPU, depending on how many cores it will have, but tends to have between 1 and 8 cores. And our cores allow multitasking. Now remember, multitasking is not the same as parallel computing. What it does is it allows us to run more than one process at the same time. I can code my program so it can use multiple cores at the same time, but for the most part it tends to be just normal multitasking. GPU, on the other hand, is very specialized. Okay, so although it is specialized for graphics, it can do other operations, tends to be focused on floating point calculations. A CPU will have 1 to 8 cores. Well, actually, a GPU could have thousands of them. Okay, floating point units will work on different parts of the data at the same time. So it uses single instruction, multiple data, and for example might perform a transformation on polygons which are part of the model. So each polygon will undergo the same calculations and each polygon will then be a process. So graphics cards, some of you might be very familiar with them. They will look a bit like this, especially the top end one. So this is a Radeon made by ATI. You can see the clock speed here. So they don't tend to be clocked incredibly high, but they don't need to be because the number of processors tends to be very high. This number here, 5.8 T-flops or teraflops, is the number of floating point operations per second. So 5.8 tera, being bigger than giga, means that it can do a massive amount of calculations per second. Graphics cards tend to have a very high memory speed on the bus, much higher than normal RAM. So they're very good at transferring lots of data very, very quickly because it needs to do that for textures and things like that in graphics. Very specialized, but those special instructions can allow us to do other computing as well. So they're very good at trigonometry operations. They have special instructions just for trigonometry. They have general floating point operations, so multiplication, things like that. And they do have some special graphics operations, naturally enough being a graphics processing unit. But it's the first two which we can use for other purposes. So problems which can make use of any of these can benefit from parallel processing, and can benefit from parallel processing, can be coded to use a GPU. So we've got two criteria here. It can use these specialized instructions and also can be programmed to work in parallel. Not every algorithm can be coded in parallel, and not every algorithm will require trig and floating point calculations. So another big characteristic of graphics processing units are that they work in single instruction multiple data. This is where we have a single instruction which runs on every single core, but on different parts of data at the same time. So they're well suited for this type of parallel working. For example, if I'm working on lots of pixels within a texture, we need to do the exact same calculation on every single pixel. So each core is going to be doing the same calculations, but on different pixels at the same time. So any problem which requires a single instruction multiple data approach and also is floating point based will benefit from using GPU. So GPUs work as a single instruction multiple data, so each core will run the same code just on different data. Sometimes you might read on the internet that single program multiple data. It's effectively the same idea. So note that GPUs do have multiple cores, but they cannot run multiple instruction multiple data. Okay, so they can't run in that kind of general way that a normal processor can. So we can use graphics processing unit for different purposes. So here are two examples of things you can do. So data mining. Data mining is covered in detail in another topic on component 2 when you're looking at computation methods. But in general, it's where we're trying to pull trends and predictions out of vast amount of data. Because of the vast amount of data, a single instruction multiple data approach is ideal for it. GPUs also have a very high memory transfer rate, and ergo those two things put together means they're ideal for doing data mining processes. Any form of modeling also works really well in GPUs because we might have lots of individual elements within the simulation. For example, if I was doing molecular modeling, each molecule would be an individual item in the simulation. Each one will run the same program because they're each doing the same things, the same interactions. Therefore, they can work on different parts of data, which are ideal for a single instruction multiple data approach. So to finish off, I've got a number of exam questions to have a look at. So I'm just going to kind of go through each of these very slowly. So a gaming company decides to release new video games. The console will use a modified version of the operating system called Linux. Describe two functions on an operating system that might be expected to carry out on the console. This is not directly linked to GPU. This is kind of more of a setup question, but just a little bit of an exam tip on this question. You need to make sure you're talking about the console. Okay, so whenever you choose two functions of operating system, i.e. two things that it does, make sure they link back to the console in some way. So for the mark scheme, you can see it says user interface, which is something we know the operating system does, but then it says to load games. Okay, so you can see it's linked back to the question. Control the hardware. For example, like the games controller or graphics card, you see it's linked back to the question. Access platform, which software can be run, such as games and apps. Control access, so different users can access systems, so security. You see every single one of these is clarified with a point linking back to the question. Linux open source. Explain how Linux being open source will benefit the games company. Again, you need to link it back to the question. As well as CPU, the console contains a graphics processing unit for 3D graphics. Explain why a GPU is more suitable than a CPU in this task. Now, for this question, you need to think about, okay, what's the core idea behind a GPU? What does it do? How does it differ from CPU? And then you can use it to answer this question. So, in the previous question, looking at the open source, means that core functionality is already available. The company just has to make amendments and changes to it, and that saves time and money. Part C, comparing GPU and CPU. General purpose, designed specifically for graphics. So that's one key difference. Also likely to have circuit instructions for complicated graphics operations. So that is specialized instructions that I was talking about. GPUs are performed an instruction on multiple pieces of data at the same time, single instruction, multiple data. Often we want to do this when processing graphics, so you can talk about any relevant example there, which means it perform transformations on screen graphics much quicker than CPU because it can do the same calculation on many different parts of the picture at the same time. Explain two reasons why games designed for companies' consoles may not work on this machine. This is thinking about the difference between operating systems, the difference between library cores, and also the difference between CPU architectures. So different consoles makers might use different DRM, okay, and that's a bit of a out there mark if I'm honest with you, but there you go. Different consoles will have different processors and different instruction sets, so that's linking back to the idea behind RISC and CISC. Different consoles have different operating systems, so games may be dependent on libraries on one operating system which don't exist in the other. Okay, so remember, whenever you develop a program, it's good to use libraries. Those libraries are operating system specific. And also, they might be on different media. So some consoles might use Blu-ray, some might use DVDs. So just a little bit of subject clarification. You need to be able to understand the purpose of GPUs and what applications they're used for. Understand that GPUs are used for graphics, but also other applications such as modeling and data mining. Candidates should also understand the benefits using and why they're suitable for certain tasks, special instructions, multiple cores, and SIMD processing.